Okay, so we are moving on to chapter 27, which is astronomy, stars, and galaxies. Um, so here's the thing that I like is that if you think of it, we have been we have been looking up to the heavens since the dawn of time. Since people were on this planet, people were looking up. And if you think about it, what's cool about that is pretty much, with the exception of the location in the sky, most of the stars are exactly the same. Think about how often you guys talk about stars and think about stars, and sometimes you take it for granted. Here's my big question: how many stars can you see in a night? Well, if you're in Pontiac, or better yet, if you're out by where I live, out in the country, you can see anywhere from 6 to 7,000 stars. But if you're in Chicago, how many stars can you think you can see there? Yeah, not very many, right? And it's because of light pollution. So maybe there are more than you can think. Maybe 30. One of the craziest experiences I ever had was when I was out in the middle of the ocean on the Pisces with NOAA, the National Oceanic and Atmospheric Administration. I was out there, and one night, uh, no moon. They had shut all the running lights of the ship off, and we were out in the middle of the ocean. And the stars and the Milky Way were so incredible. Now, granted, the ship was going up and down, but to see them with no light from anywhere, no cell phone towers, no buildings, no cars coming down the road, not a plane in sight, right? And so to see the stars, and for me, I love the stars. If you think about the history of humans, you know, before we had TV, before we had any other stuff that takes up our time, what did people do? They sat and they looked up. And that's what stars and galaxies are. So, what are the objectives for what we're doing? So, our first one is we're going to describe how astronomers determine the composition and the surface temperature of a star. The second one, we're going to explain why stars appear to move to you or an observer on Earth. We're going to name and describe the way astronomers measure the distance from Earth to stars. It's not like we've got a big old ruler that we can take and we just stretch it out to see where we're at. And then we're going to explain the difference between absolute and apparent magnitude. So here's how we're going to get started. Characteristics of stars. Number one, we got to look at temperature and composition. Well, it's not like we can go put a thermometer in the star's mouth. It's not like we can go and do that. So what we do is we use a spectrometer. Now, earlier this year, we got to play with spectrometers, spectroscopes. We got to pull them out, and we got to see the lines. Those lines by looking at a light source. We did it with different elements. We did it with hydrogen and helium and neon and argon and krypton and all that. And so we look at the spectra, what's called a dark line spectrum, to determine what elements are there. That's the best part. We can figure out what elements are in that star by looking at it with our spectroscope. Now, it's a little bit more technical than the spectroscope that we used, but ours was pretty simple, but it did work. So then, if you look at your table in your book on page 547, go ahead and take a look at that at this time. You can open that up real quick. It's easy. Page 547, table 27.1. What you'll see is on the table, we basically have colors, right? The bottom color being what? Red, right? The top color being blue. Now, if you look at the first blue-white, right? It says red, orange, yellow, yellow, white. The first blue-white should be white, then blue-white, and then blue. It's a typo in there. But what is interesting about this is when you look at them, you can figure out what temperatures do what. So here's what I mean by that. Ready? So here's the thing. When I was a kid, I used to love to go camping. We don't do as much camping as we did back then. We go camping a little bit different. I sometimes refer to it as glamping now, like glamour camping, like we're in our trailer. Whereas before, we just sat outside and we had a campfire and then we slept underneath the stars. That was what I did when I was a kid. Well, what we used to do is to see if we could get a fire really, really hot. And if you think about it, these colors that are on that chart are just like your campfire. So if you get a raging campfire, it's going to be what they call it a white hot, right? It's going to be a white color. Now, I'm not talking about throwing those little crystal things in the fire to change the color of your campfire. But if you get it really, 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 really hot, it's white. If it's not, in other words, if it's a cold fire, which is a contradiction in terms, but if it's less heat coming out of the fire, guess what? It's kind of a dull orangey red, right? And so if you look at your not your periodic table, but the table on 27.1, if you look at it, you go, oh, it makes sense that a red star is less than 3,000 degrees and a freaking blue star is 30,000 degrees plus. Right? Think of our campfire. A real hot, raging campfire is that white, bluish white. A not so hot campfire is more of an orangish color. So if you think about it, it makes a lot of sense. So hottest ones are blue, coldest ones are red. Hottest ones are blue, coldest ones are red. Okay. So what color is our sun? When you take up and look at our sun, when you look at our sun, what color is our sun? Our sun is orange. Our sun is orange. And so if you think about it, orange is yellow. Is our sun hot? Well, we don't know yet. But according to this chart, where would you guess where our sun is? Well, I would say our sun is about 5,000. If you look over there, do you see the word sun on the chart? Yeah, it says sun, right? Our sun, hey, guess what? It's orangish red, maybe orangish yellow, right? Our sun, right there, 5,000 to 6,000 degrees. Yeah, that's where we're at, right? So makes sense using that chart to figure out where it is. Now, when you guys look up at the stars and look up the sky from Earth, the closest star is what? The sun. That's right. 93 million miles. But here's the deal. You're close enough to see that color. When you just look up and look at white, you're like, oh, a little twinkle, 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 little star. There it is. You can't tell what color it is. So they have to use a really, really high-powered instrument, telescope, maybe the Hubble, spectroscope. So again, our temperature about 5,800 degrees on our sun. So motion. So what I've got you going to is page 584. 584. And so on page 584, that's the wrong number. Sorry about that. So on page 548. Sorry about that, my dyslexia. 548. I'll change that. Figure 27.1. What do you see? It looks like streaks in the sky, right? It looks like streaks. And what's caused that is somebody has taken a camera and they've held the shutter lens open. And basically, now this is my favorite. People say, oh, the sky moved. Well, people, we're the ones moving. The sky's pretty much staying. It's moving out there too, but from our vantage point, we're the ones that are moving. And it's because we are doing what? We're rotating on our what? Axis. Yeah, our axis. Very good. So, due to the rotation of the Earth, we are appearing to move around Polaris, or the North Star, right? We are moving westward around the North Star. So if we go up by the North Pole, open up our camera, have it pointing at Polaris, and you do it right, you can get this beautiful circle of all these stars. It's like really hypnotic. It's cool. So again, when we look at the stars, if you go out at night, you go out and look for a star. If you go a little bit later, it's going to probably appear to move to the west because we are rotating. No different than if you think about when the sun comes up, it does the same thing, right? All right. Talked about the pole. What's a pole? Pole is where that imaginary line that goes right through the center of the earth, or where Santa Claus lives, right? And so what happens is, if we're spinning on that axis, like I just talked about, we're spinning on this thing, we refer to, if you can see a star visible all year long, that star is circumpolar, right? And so for me, I put up here Ursa Major. Anybody know what Ursa Major is? It's a constellation. Does anybody know what it is? It's the Big Dipper. Yeah, the Big Dipper. Ursa Minor. Anybody want to guess on this one? The Little Dipper, right? Cassiopeia, one of my very favorite. Oh, I love Cassiopeia. It's a W in the sky, and it's really really cool. And so you see this W. It's up all year long. Very cool, very beautiful. We'll show you that a little bit later. So the actual motion, right? So we have apparent motion, what it looks like it's moving, right? And then the actual motion. And so for us, if a star is actually moving, and they rotate just like we do on their axis, right? And so I want to show you what I'm talking about here. I'm going to push stop for a minute on this, pull up this, and go to my good friend Google. So if we look at our sun rotating, here's kind of what it looks like. And so our sun rotates, and it rotates on its axis just like we do. Now, you'll notice as ours is spinning, some really cool stuff. Now, that wasn't the sun. That was the telescope that they're viewing. Don't get sick here. Hold on. There we go. Back to normal. The telescope that they were viewing this with rotated. So again, this is rotating on its axis. Good view, good look, and they are actually moving. So out in outer space, you got stars that are rotating. This one happens to be our sun. Okay? So we have stars that are actually rotating. Okay? Then you have them traveling through space as well. And so if you think about it, they're moving as well. Sorry about that. They're moving as well. And so we're moving, they're moving, other planets are moving, right? And so they are constantly traveling throughout the universe. All right. So actual motion. Again, whether or not they're coming to us or going away, their colors, we talked about this early on this year, that their colors will either be red shifted or blue shifted depending on the direction they're coming to us. And what we know is the stars that we see and the galaxies that we see are predominantly red shifted. Why? Because they're going away from us, right? We're expanding as a universe. So, again, most of them being red shifted. Uh, so, how do we figure out the distance to a star? The distance to a star is calculated is if we could travel the speed of light, how long would it take us to get there? Now, the speed of light is an insane number, and nobody could ever reach it because as you got to the speed of light, right? Time elongates. But think about this: how many of you have ever heard a loud noise and it's like way away? This is my favorite thing. I'll be at the golf course with my team, and I'll be down by the green, and they'll have the guys on the tee box, and all of a sudden you'll see them swing, and then you go, and you'll hear it. So you can see them swing, and then they hit it. And so that actually the sound and the light went the same time, but it took a lot longer for the sound to travel to you. Yeah.
We've been able to beat the speed of sound, but we have not been able to beat the speed of light.
We can surpass the speed of sound. It's called a sonic boom, right? We can do that, but we can't even get to the speed of light. So the light year is a distance that light travels in 1 year. About 9.5 trillion kilometers per year. This is one heck of a road trip. Yeah.
That kind of happened to me. I remember I was on the phone with a friend. She lives on the other side of town, and it was thundering, and I heard the thunder over her.
Sure.
Over the phone.
Sure. So that happens a lot. Thunder's a good example, right? So you'll see the lightning, and then you'll wait and you'll wait, and then you'll hear the thunder, right? Same good example of that. So if you think about this, I changed this number into a number that you can identify with. So it only travels 186,000 miles per second. Hang on, ready? Seatbelt. Right? No, I don't think so. That's insane, right? So to travel the speed of light is impossible. Now, think about this. It takes about 8.5 minutes, like 8 minutes and 20 seconds, something like that, for light from the sun to reach us. It's 93 million miles away. So, right now, here we go. Ready, set, go. If the sun were to have burned out right there, exploded, just like that, gone, see you, bye. It would take 8.5 minutes for everything to shut off. No light. And that's unbelievable because it's so close. Now you're going, 93 million miles is not that close. Oh, but it is. That's the nearest neighbor we have as far as a star. So our sun, the next one from us is Proxima Centauri at 4.2 light years. So it would take us 4.2 light years traveling at the speed of light for us to reach Proxima Centauri. Here's the problem with us trying to find other places to live, right? I was like, oh, we'll find another planet. We'll hang out. It's going to be great. No. It would take traveling at the speed of light hundreds and hundreds and hundreds of years to get there. Our best bet, by the way, right now is Mars. Polaris, Polaris, the North Star, it's only 700 light years. I love this. This again is apparent motion. Apparent motion. This picture was taken close to the North Pole. Not exactly, because if you look at the middle, that big white light, that's Polaris, and it wasn't exactly, but it's pretty darn close. When you get a bunch of stars together, they all hang out, like share Pinterest tips and stuff like. No, they don't do that. It's a galaxy, right? And we're going to talk about galaxies as well. Some of the most beautiful things. Take a look at tonight's sky. Look out there. You'll see the Milky Way galaxy. We're a part of it. You see the white light going across us. Depending on how much cloud cover is out there, you'll see it. This is one of my favorite. If you look at this, the Horsehead Nebula. It's called the Horsehead Nebula. Nebula is a really cool way of saying gas, right? And so this nebula, Horsehead, looks like a horse head right there. So you got some stars right here being coming through, and then the nebular gases right there. Ooh, the bubble nebula, right? So you look at these, and these were taken with the Hubble Space Telescope. How do you know that HST is Hubble Space Telescope? Bubble nebula, these gases are forming a bubble. You got a star here, and then you probably got some baby stars cranking over and becoming stars. Again, this is another nebula here, and you can see all these really, really big lights. There are probably other galaxies as well. I love this. Eta Carinae. Basically, you've got a star in here, and this is, I believe, X-rays given off by this thing. Here's a galaxy on its edge. So all the stars are whizzing around this thing, whether it's clockwise or counterclockwise, I don't know, but are going around this galaxy right here. Here's another galaxy on its edge. Okay, parallax. This is where it gets interesting. I want everybody to take your right thumb and stick it in the air. Not your middle finger, your right thumb. Very good. There you go. So we are constantly changing our view of where we're at. Still got that? Still got that thumb up? Here we go. And so we are changing our reference. Now here's what I want you to do. I want you to close one eye and then put your thumb on a person's head across the room to where you can't see their face anymore. On the count of three, I want you to change your eyes, shut the other one, and open the other one. 1, 2, 3. They jumped. Yeah, they moved. Well, they didn't really move. It's the fact that there's a distance between your eyeballs. And so when you do that, that change is called parallax. Not a paradox, parallax, right? So again, you're holding your eye and then switch your other eye open and you can tell, oh, yeah, it's moving. Well, that's the distance between your eyes. Well, we use the same principle when it comes to figuring out where stars are, right? Parallax. So what we can do is we can let me show you a picture here. So here is a parallax. So if you look at this image right here, say we are, I don't know, wherever we're at. So when you're closing one eye, okay, it's the same thing. It looks like the image has moved depending on where you're at. Small parallax, again, it looks like the image has moved a shorter distance just because it's further away. So again, parallax, just like you just did with the people across the room, same thing. All right. Stellar magnitude. So stellar magnitude, how big, how big, or how bright, I should say, are stars. So if you look at a star, unaided eye, how bright is it? Right? So we can see about 6,000 here in Pontiac. If you have a telescope, ground base, about 3 billion. If you go to the HST, about 1 trillion. Not bad. So apparent magnitude. I always say this. Apparently he doesn't like me, or apparently you really enjoyed that, right? It seems like, right? Well, apparent magnitude is the what it looks like from Earth, what it appears to look like from Earth. And so that is what we refer to as apparent magnitude. Okay? Now, some stars are bigger and some are smaller. And so we use a scale -30 to 29. Negative is the brightest. So currently in our nighttime sky, or in our sky, I should say, the sun, it's a -26. That's the brightest. Well, why do we do that? Because the sun is really a good object for us to gauge from, but it's so close. Right? It's right next to us. It's so bright that we can see daylight, right? And if we look at the faintest ones, -29, you can't see it unless you have a telescope. Okay? So brightest to us would be a negative, dimmest to us would be a positive. Absolutely. Absolutely. How do you feel? Absolutely wonderful. I really do. Right? Absolute magnitude. Take the distance and then how bright it really is. Right? So we use this by calculating a distance of 32.6 light years. What we're trying to do is measure them all at the same distance. We refer to that as 10 parsecs, by the way. So 32.6 light years, we're going to look at every star as if they're 32.6 light years. So we compare them. If we compare them at 32.6 light years, in other words, we get away from our Earth, or the sun, it's a 5 magnitude. Not very good. It'd be not very good, right? So if you look at all from the same distance, then you can compare them. Well, if we move all of them to 1 parsec, which would be 3.26 light years, okay, then they're all going to get brighter. So the absolute magnitude is going to be brighter. So if you look at how close the star is versus the absolute versus apparent magnitude, then you'll see there's a big difference, right? There's a big difference. And that's on page 27.5, figure page 533, maybe. I love this. Betelgeuse. 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 If you say Betelgeuse 3 times, he's supposed to appear, and then all crazy stuff happens. This is actually Orion the Hunter. You should see it tonight in your nighttime sky, looking straight south from where we are at right now. Well, Betelgeuse is a huge star. Look at the size of Betelgeuse. Look at the size of Earth's orbit. Look at the size of Jupiter's orbit. This star is bigger than the orbit of both of them put together. This stinker is huge. But you don't see it you see it, but it's not really, 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 really bright. Yeah, very far away. Here's our sun. Here's some solar prominences and flares. We'll talk about that. This is our sun again. And so we're going to stop there. So what I want to do is stop here. We'll pick up here. I'm going to have you all right, here we go again. I got to figure out how to shut this thing off. So with that being said, I hope you've enjoyed it, and it's not shutting off. If I've just been doing that for nothing, I'm going to be upset. Well, that went well.
She told me to tell you to look at number 50 and 30.
Okay.
Because she said one of them said that you might have crossed out the right answer. What'd you do?
He broke his computer. After doing Camp Studio. You missed the lesson.
You can't see it, can you? Let me just go and put this on back in.
Yep, please. How do I shut Cam Studio down? No. Yeah, it's flashing green at me. No, the whole screen. It's like I'm going to go into an epileptic seizure. I wanted to, but I couldn't shut it off. It wouldn't come back up. Yeah, I'm sure it is.
I think you might just want to reset.
Okay.
Oh, nothing. Okay. Yep. Okay, I'll call Amy. Thanks.
I have a present for you.
Thanks.
Hello?
My screen is flashing green because I can't get out of Cam Studio. Can
Okay,
I don't know what to do.
okay. Is that all? Yes?
Yeah.
Okay. Okay, bye.
Thank you.
Especially Trippy. You want me to get in there and make it work?
Really nice.
I don't think it was recording.
It's not in there. I looked for it. Dylan, which numbers?
30.
Okay.